Hello friends, today we will start discussing sampling. In this lecture, we will discuss ideal sampling, which is also known as instantaneous sampling or impulse train sampling. In the previous lectures, we saw the block diagram of a digital communication system. The first block in the transmitter of a digital communication system is a source encoder. If the message signal happens to be an analog signal, then the source encoder has to first convert it into a digital form before doing subsequent processing to remove the redundancy from it. But the first job will be to convert the analog signal into a digital form. And that is what we saw in this extension of the source encoder block, which comprises a sampler, a quantizer, and a discrete coder. Here, the input is assumed to be an analog signal, and therefore it is written as input waveform. An analog signal here is the one which is continuous in time as well as continuous in amplitude. Continuous time, continuous amplitude signal. The sampler converts the continuous time part into a discrete time part. That is, it discretizes the time signal on time, whereas the job of a quantizer is to convert the continuous amplitude part into a discrete amplitude part. So the output of a sampler is a discrete time continuous amplitude signal, and finally the output of a quantizer is a discrete time discrete amplitude signal, which we also call as digital signal. Thus, these two blocks, sampler and quantizer, together function as an analog to digital converter. Okay, so these two together function as an A to D converter. This analog to digital conversion is a basic operation required for digital communication. And the first step to achieve analog to digital conversion is to discretize the signal in time, and that is achieved by a sampler, and the corresponding process is known as sampling. So the process of sampling can be defined as the process of obtaining a discrete time signal from a continuous time signal. That means to say, suppose we have a signal like this. This signal, say m of t, which is a function of time, it is continuous in time, meaning that it exists for all time instants, and it is also continuous in amplitude. That means it can take on a continuum of values in a given amplitude range. Thus, it is an analog signal. So, the process of sampling is to obtain the samples of the signal at some desired time instance, say some reference 0th time instant, then some ts time instant, some 2ts time instant, similarly for negative indexes minus ts, and so on. So what we actually want from this m of t, we want to get the sample values at t equal to 0, at t equal to ts, at t equal to 2ts, at t equal to minus ts, and so on. So to achieve only a discrete set of values at t equal to 0, ts, minus Ts and so on is known as sampling. So how can we do that? It can be done through a process of what is called ideal sampling or instantaneous sampling or impulse train sampling. Or there are some practical ways of doing it, which includes what we call flat top sampling, which is also known as sample and hold sampling, or also known as pulse amplitude modulation or PAM. Another way of doing sampling is what is called natural sampling. In this lecture, we will focus on the process of impulse train sampling. So let us understand impulse train sampling. Let us assume we have a continuous time, continuous amplitude signal m of t as shown here. In order to obtain the samples of this m of t, we claim that if we multiply this signal by an impulse train, a periodic impulse train is a sequence of impulses, impulse functions, each separated by an interval of Ts. Say this is 0, this is Ts, this is 2 Ts, this is minus Ts, and so on. The strength of each impulse is unity. And let us denote this impulse train by delta sub Ts of small t. If we multiply these two signals, m of t multiplied by this impulse train, we claim that the resultant signal would be the samples of the original signal m of t. Let us try to see this mathematically. Let's say the resultant of the product of these two signals be denoted by say m sub delta t. So it denotes the product of these two signals, that is m delta t equal to mt into delta ts of t. Now, how can we represent this impulse train mathematically? It's very easy to understand. Now, what is this impulse at t equal to 0? The impulse at t equal to 0 is written as delta of t. What is this impulse at t equal to ts? This impulse at t equal to ts will be denoted as delta t minus ts using the shifting. Similarly, the impulse occurring at t equal to 2 ts will be denoted as delta t minus 2 ts. The impulse occurring at t equal to minus ts will be denoted as delta t plus ts. In general, the impulse that occurs at some integer n times ts will be denoted as delta t minus n times ts. And because the impulse train contains all such impulses, so we will have a summation. So n equal to minus infinity to infinity delta t minus nts. So this is how we denote this impulse train mathematically. Now, this m of t doesn't depend on n. So it does not matter whether we write it outside the summation or inside the summation sign. Let us bring it inside the summation sign. So n equal summation n from minus infinity to infinity m of t delta t minus n ts. Now here we invoke a property of impulse function. So let us recall a very important property of impulse functions, that if we have some signal x of t and it is multiplied by delta t minus t naught, some t naught, then the result of this product will be x of t naught, that is the value of the signal occurring at t naught, into delta t minus t naught. So using this property of an impulse function, we can see here that m of t times delta t minus nts can be written as m of nts into delta t minus nts. And this is a very important result. What does this result indicate? Let us highlight this result. This result indicates that m delta t is again a train of impulses, delta t minus nts, where the strength of each impulse is given by m of nts. And what is m of nts? M of nts is the value of this signal m of t at the time instant n times ts. For instance, when n is equal to 0, m of nts will be m of 0, that is the value of the signal occurring at 0, t equal to 0. So this is supposed to equal to 0, so we'll get this value. Similarly, when n is equal to 1, m of ts will be the value at t equal to ts. When n is equal to 2, we will get m of 2ts. That is the value of the signal occurring at 2ts, and so on. In general, we get a signal which is nothing but a train of impulses where the strength of each impulse, strength is the area under the impulse function, which we denote by this arrow. So strength of the impulse here at t equal to 0 is equal to m of 0, that is the value of the signal at t equal to 0. The impulse occurring at ts, capital Ts. So this is the value of signal at m of ts. Similarly at 2ts, the value of the impulse here, the strength of the impulse here is m of 2ts. Similarly for negative time instants, minus ts, the value of the impulse, the strength of the impulse will be m of minus ts, and so on. So what we get if we multiply this continuous time, continuous amplitude signal with an impulse train, a periodic impulse train with the period ts, then the result is another impulse train, each separated by ts interval, but with the strength of the impulses equal to the value of the original signal m of t at those instants where the impulse occurs. Thus we see that we can discretize a signal in time by multiplying it with an impulse train. This is what is summarized here again, that we had a continuous time, continuous amplitude signal m of t, which when multiplied by the impulse train results in the signal we denote by m delta t, which is an impulse train with impulses separated by ts, and the strength of impulses given by the values of the signal m of t at instants where the impulses occur. Here, this ts is called the sampling interval, and its reciprocal 1 by ts is known as the sampling frequency. The sampling frequency is frequently denoted by f subscript s. Now, what we have shown here is that it is possible to obtain the samples of a signal by impulse train sampling. But a very important question here we would like to ask, are we not losing any information because of sampling? Because the original signal, the original information existed for all infinite possible instants of time, because the signal was continuous time signal, and now we have taken the samples. We are only collecting the signal values at some discrete time instants. Are we not losing information in doing so? In other words, can we exactly represent a signal just using its samples? Or equivalently, given the samples of a signal, can we exactly reconstruct the original continuous time signal? These are some questions of fundamental importance in digital communication as well as digital signal processing. We would like to answer these questions in the next lecture. Thank you.